Right. So this period, there are a lot of students who are at CISPIS. So you notice little recorder going down here. So I'm recording this right now. And then if you're on YouTube, no, Aaron cannot say hi, but that's going to be on the video now. And so they're going to have access, and you're going to have access to this video as well. It's going to be on that same page on Schoology. So Coulomb's law has to do with what happens when you've got an electrical field. Electrical fields are created when objects transfer electrons. So we're going to go from the big macroscopic idea of the universe all the way back down to the atomic level. And in order to do so, we're going to have to remember the difference between field and contact forces, understand the idea of what an electrostatic charge is, which is actually a really fancy name for just transfer of electrons, and show how the electrostatic charge of two particles relates to the distance between those particles and the magnitude of the charges. Now, I want you to think for a second. Think of Newton's U-log equation. Doesn't that do the exact same thing? Compares the magnitudes of the masses to how far those masses are away from each other. So they do the exact same thing. So, quick review. Contact forces. Those are forces that occur when a force causes another object to accelerate. So if you go from rest to having a velocity, you're obviously accelerating, and if you push something in order to do it, you've applied a contact force. So applied forces are contact forces, friction forces are contact forces because two surfaces touching each other, tension forces are contact forces because it's a rope pulling on something. Yes.
Who is Coulomb? Is that a guy?
That is a guy. He's coming up. Charles. Unfortunately, in the 1800s, it was mostly old white men that did this, so it was a good assumption. Field forces. So those are forces that cause something to accelerate without having to touch it. And we haven't delved into those except for gravitational force. When we're looking at Coulomb's law today, we're going to be looking at electrical force. We already know that gravitational force can be calculated either using Newton's law of gravitation or a drawn planet Earth, F equals ma. Today we're really just going to focus on electrical force. Magnetic force is also a thing, but we're not going to talk about this today. So those are three examples of field forces. You may have these written down back in your notes way back in November. I think that's when we started forces. Somewhere in there. And don't forget, this is also going to be on Schoology, so if I'm going a little bit too fast, don't panic. I'll go back and it'll be on Schoology for you. All right, now we're going to hopefully review a little bit of physical science. I know that if you're in honors physics, there's a high potential you took physical science in 8th grade. Anybody not take physical science? Okay, well then this is easy new information anyways, not a big deal. So, all matter is made up of atoms. That really does matter quite a bit. See, now Aaron's on the tape again, and that's not good. And so all matter is made up of atoms. And hopefully this sounds familiar to you. There are three main subatomic particles inside of an atom. Protons, neutrons, and electrons. Has anybody never heard that before? Protons, neutrons, electrons. Very good. That's the most important thing with physical science you need to remember today. Protons have positive charges. and live in the nucleus. And electrons have negative charges, and they live outside the nucleus. Neutral atoms have the same number of protons as electrons to balance each other out. So, for example, hydrogen has one proton in the nucleus and one electron outside the nucleus. So when I say protons and electrons have charges, we can actually measure the quantity of that charge by putting those charges next to each other and seeing how much they repulse each other or attract each other. And the other piece on here, it says energy levels. How many people are taking chemistry next year of some sort of persuasion, IB or not IB? So, how many people have taken chemistry before? So, you may remember that there's 7 different energy levels inside of an atom. There are 7 different energy levels. Hydrogen is the smallest atom on the periodic table, and it only has 1 energy level. And you're going to learn all about that next year. And Will is going to tell you how much fun it is, too. He's going to talk about it. All right. As I already said, a neutral atom will have the same number of protons as electrons. So since protons are positive and electrons have a negative charge, they attract each other. Positives attract negatives, or negatives attract positive. And that force of attraction can be measured with Coulomb's law. So it's interesting to think, if I've got this atom, and I've got an electron out here, and a proton in the center, and they attract each other, you'd think that the whole atom would collapse in on itself and combust, because those 2 charges are attracted to each other and the atom would implode. That does not happen because of the presence of a neutron. And neutrons are like Switzerland. Neutrons live in the nucleus with the protons, and they act just kind of like a bodyguard to keep the protons away from the electrons. Neutrons are exactly as they sound, neutral, they have no charge. Now, why I'm telling you all of this is because remember we're going down to the microscopic or nanoscopic scale where we're talking about atoms. And we're remembering that each one of those protons and electrons each have its own individual charge that can be measured. Yes, Evan?
So hydrogen only has 1 proton and electron.
Right. But there's 3 versions of hydrogen. The main isotope of hydrogen has no neutrons. And the reason why that doesn't collapse in on itself is because the first energy level is so far away from the nucleus, it doesn't actually converge. As you increase energy levels, the energy levels get closer and closer and closer together. And there's a lot of other stuff that goes on, but you'll learn all about that next year. All right. So my recommendation is this. I would say wait until the video is uploaded to Schoology to copy down this table. I wouldn't take the time to write these things down now because I'm going to show these to you at a different place in the presentation. And I'm going to skip how these charges are actually calculated. But protons have a charge, and that charge is measured in what's called the Coulomb, named after Charles Coulomb. And we say that a proton has a charge of 1.6 times 10 to the negative 19 coulombs. It's just a measure of electricity. Just take a Coulomb as a measure of electricity. Kind of like a volt, kind of like an amp, but even a heck of a lot smaller. Notice that electrons have the same magnitude of charge, but just opposite. So the proton's positive 1.6 times 10 to the negative 19th. The electron is negative 1.6 times 10 to the negative 19th. They're just opposite. And neutrons, again, have no charge. And then you see here the masses of these things. So you get the mass of a proton is 1.67 times 10 to the negative 27. And electrons are 4 times smaller than the protons, or sorry, 10,000 times smaller than the protons. They have a mass of 9.11 times 10 to the negative 31st kilograms. Again, those values are going to be on the video. I would just recommend waiting until it's uploaded and they'll be there for you. So, here's the big takeaway here. I know that Charles Coulomb said that the force between two charges can be measured if we know the quantity of those charges and the distance they are away from each other. So I'm going to show you the formula now. And what I want you to get from this is exactly how similar Coulomb's law is to Newton's U-law equation. I'll even zoom this in a little bit. So how is this equation here that I'm showing you the same, or how is it different? How is that similar to U-log? It's over R squared, right? So it's the relationship between the force and the distance is going to be one of those inverse relationships again, where you've got the radius squared in the denominator, just like the U-log equation. What else is similar here? Alex?
You have constant.
You got a constant. The constant's different. The constant's different, but you do have a constant. What else is similar?
The two magnitudes multiplied together.
Exactly. So in U-log, we multiply the masses together. In Coulomb's law, we multiply the charges together. So this is kind of a generalization for all field forces. All field forces, we can find the magnitude if we know the magnitude of the force, if we know the magnitude of the masses or the charges, and we know the distance those are away from each other. So field forces all kind of follow the same general rule, where we can calculate the magnitude of the force if we know the magnitude of the charges or masses and how far away they are from each other. And it doesn't matter if I'm on the atomic scale, really small, or I'm in the universe and I'm trying to figure out the force between the sun and the next closest star. The relationship's still the same, just the constants are different, and the size of the charges or masses are different. So here's Coulomb's law. Electrical force, which is your field force, is equal to K sub C. K sub C is your Coulomb's constant, times the amount charge 1 will register, times the amount charge 2 will register, divided by how far apart those charges are squared.
Is the radius in meters?
Yep, radius is always in meters, just the same way as U-log. Force is in newtons. The only thing different here is that the charges are measured in coulombs. In Coulomb's constant is just a proportionality constant that cancels out all the units that you don't want. So the reason why I'm introducing you to Coulomb's law during the circular astrophysics unit is just to show you field forces behave the same way on the atomic scale or the astronomical scale. They're the same. They have the same relationships, no matter where you go. no matter how small you are, how large you are. So we use Coulomb's law the exact same way as we use U-log. We just rearrange the equation to isolate the variable we want, and we solve for what we need to solve for. And the last thing is an example problem. Ready to try an example problem?
Not yet.
Not quite yet. I'll say one more thing here, that the charges don't have to be protons and electrons. As long as you see the charge in coulombs, that's going to be your Q value. Because you can have a lot of protons and a lot of electrons. All right, example equation, or example problem. Hydrogen atom has a Bohr's radius, and the reason why I'm saying Bohr's radius is because the location of an electron can only be predicted, it can't be actually calculated, and that electron is going to be always different distances away from the nucleus. So when we get the average, we call that average of Bohr's radius.
Is that the uncertainty principle?
It is the uncertainty. It's Heisenberg's uncertainty principles. So a hydrogen atom has Bohr's radius of 5.291772 times 10 to the negative 11th meters. What is the electrical force exerted between the proton and the electron in this atom? So, do I need to rearrange this equation to isolate any variables? I do not. I already have force by itself on the left-hand side. So all I got to do is just basically plug things in. So K sub C. A lot of times you'll see K sub C here, rounded to 10 times 10 to the 9th, because this is so close to 9, 10 times 10 to the 9th. This is so close to 9, it's going to be 9 times 10 to the 9th. So you can do that too, and that's absolutely fine by me. And then you need the charge on a proton and an electron. And they're exact same magnitude, but different signs. And I go back here, and I realize the proton is 1.6 times 10 to the negative 19. Electron is the exact opposite of that. And then I need a radius, and I got this radius here, the Bohr's radius. All right, grab your scientific calculators and practice again that scientific notation, putting it into your calculator with appropriate parentheses. I could treat this whole thing like a big fraction as well. Multiply the numerators together, get that answer, and then divide by that quantity squared.
Use 9. Okay, I use 8.9. Yeah, 8.13.
So thumbs up once you think you have the right response. Awesome.
Use 9. I do.
I see you, Grace.
Use 9.
Yeah, you don't always know.
No.
Anybody struggling putting it in? Thumbs up once we got the right response, you think? Okay, got it. Good, good. The answer should be negative, I'll give you that good.
Except for the couple.
No sig figs in this because they're all literature values.
You have to do 18.
So going out to the 100 spots, kind of the rule of thumb. That is a news. Okay, I'm going to write my answer. See if you agree. Agree?
Yeah.
Okay. So here's something strange about chemistry. If the value is negative, it means there's an attraction because you are having the proton being attracted to the electron, so it's going towards the electron, so the force is negative. Negatives are kind of positive in chemistry. So if you've got a negative force, you've got an attraction. If you've got a positive force, you've got a repulsion. It's one of those things you have to get used to. It's because just remember that electrons are negative, and that's the reason why. So there you go. That's basically how Coulomb's law works. Coulomb's law is the exact same thing as U log. The only difference is your proportionality constant, and that you're using charges instead of masses. You could take this one step further, and you could actually calculate the gravitational force between the proton and the electron. You could actually calculate that because you get the masses as well. And you might be asked to do that eventually. So, to prepare you for any sort of Coulomb's law question you're going to see on any sort of assessment, or in chemistry, or in life. But, well, you might. Depends on your line of work. There is that punny worksheet there. I think I put down 1 through 14. 1 through 14 only. 11 through 14 only, thank you. Yes.
That's a lot of
I can pull that up. Let me stop.